So today we're going to look a little bit more at surfaces. We've been building our surfaces as functions. We start with the simplest construction. We start with the most restrictive function, construction. That is, writing one variable as a function of the others. So if we have a function of two variables, we know we're going to have a surface in R3, but we want to note that there are still three variables running around. When we write our function of two variables, there's still the dependent variable. So there are three variables running around. So we could more generally describe this as an equation in three variables. The first ones we looked at were our favorites, linear functions or linear equations, where all the variables only have degree 1. So we have a degree 1 equation. That means the exponents are all 1. And we don't have any degree 2 terms like an x times y. So even though the x and the y factors might have degree 1, if we multiply them together, that would be a degree 2 term. That's not linear. We have multiple forms. Our function form is like point slope or slope intercept, where we're solved for one of the variables, but we can just rearrange to write an equation in three variables to get a standard form. And we can even get rid of our fractions, which is kind of a standard thing to do, because we all tend to be fraction haters for some reason. Bunch of number racists. Like, I don't like fractions. Why do you have to have two numbers? I want everything to be out of one. All right. So one of the interesting things about this rearrangement is that we get the thing that we get to see something that we haven't really seen before. So when we look at the slope-intercept equation, all the numbers represent something that helps us describe what's going on. In the linear equation, all the numbers in the slope-intercept form are telling us something. Like in this point-slope form up here, this line contains the point -6, 5, and has a slope of -2/3. We have a complete description of what's going on in this equation. We can see one of the points that's there, and we can see which direction it's going. That's the only two things that we need for a line: a location and a direction. To describe a plane, we have a location. This number is telling us a location. Z is 7 when x and y are both 0. And we have two directions because we're describing a plane, not just a line. It's two-dimensional. So this 4/5 is describing the direction in the x direction, and the -2/3 is describing a tilt in the y direction. Now, when we look at the standard form, 2x plus 3y equals 3, or 12x minus 10y minus 15z equals -105, we don't see those numbers in that description. They don't jump out at us, obviously. So we want to today look at what the 2 and the 3 are telling us. So what do the coefficients in the standard form tell us about our line or our plane? This is one of the things that we're going to be interested in. What do the coefficients in standard form tell us about the line or the plane? All right, let's take a look. So let's draw a picture of this line. 2x minus 3y is equal to 3. So we're going to go through the point -6, 5. -6, 5, let's see, is here. And the more important part is the direction. The line has a slope of -2/3. So I'm going to drop down 2 and go to the right 3. Drop down 2 and go to the right 3. So there's our slope of -2/3. We go down 2 and right 3. Or we could think of going the other direction where we go up 2 and then left 3. So it could be a +2 and a -3 if we're just going the other direction. That just changes both the signs, which doesn't change the sign of the slope. So here we're describing the slope with one number because we can. There's just a rise and then a run. We summarize that in the slope with one number. The next thing that we want to look at is we want to think about describing this direction, not with just one number, but with our more standard way of describing direction. The normal way we describe direction, especially once we get out of R2, is to use vectors. So we want to use vectors to describe direction. So we want to describe this, the line with the slope of -2/3. We want to describe that direction with a vector. And so here, let's write a vector. We just say how much x we're doing. That came out badly. We just say how much x direction change and how much y direction change. That was a little bit more PG. So I could say here's a vector that's describing this line. And we can say that this vector, say v for vector, is the vector. We've gone -2 in the x direction and +3 in the y direction. Sorry. I was rise over running. We've gone a +3 in the x direction and a -2 in the y direction. So one way we can describe vectors is make them look like points, but we want to make sure that they're vectors, so we put the pointy brackets on. This is a fairly common way to describe vectors. Keep wanting to make 2 in the x direction. We have lots of choices in how we describe vectors. Notice that this is not the only way we could describe what's going on in this, describe this direction. Here I'm saying the line is reading from left to right, but we're just trying to describe a direction. So it's also possible to describe this same line with a vector going in exactly the opposite direction. In which case we're going a -3, but now a +2. -2 divided by 3 is the same as 2 divided by -3. They're both -2/3, so I'm describing the same line, just with different vectors going in opposite directions. Now, what we want to notice is that the 3 and the -2, the 3 is going with the x, and the -2 is going with the y, or the -3 is going with the x, and the +2 is going with the y. These two do not show up in the standard form. The standard form has a 2 with the x and a 3 with the y. So that seems backwards. That's because the coefficients in the standard form are not telling you the actual direction of that vector. The coefficients are telling you the direction of a vector perpendicular to the line. The coefficients in standard form are of the perpendicular vector. So instead of a -2/3, the perpendicular vector will be a reciprocal and an opposite. So I'm going to do a +3 and a +2. So a slope of 3/2 is going to be a change of 3 in the y direction and a change of 2 in the x direction. And now the components, words hard today, the components of the normal vector or the perpendicular vector, they do show up in our standard form. So the coefficients in standard form are the components of a vector normal to the line or perpendicular. Yeah. Yeah, this one over here is in the XY plane. That's why it seems so weird that we would be describing a line with not its direction. The reason that we haven't, it's not often pointed out when we're doing algebra that the coefficients of in the standard form tell us the components of the normal vector is that we're usually learning about lines way before we're learning about vectors. Then we learn about vectors, and we don't go back and point out that the components of the normal vector will be the coefficients in standard form. But the reason I want to point it out is that I can draw this, and then we could look at this standard form over here where we have a plane. Here we have a plane, and the coefficients in the standard form tell us a vector that is normal to the plane. And that, in R3, is a good way to describe an entire plane. Instead of saying the plane is the span of these two vectors, we can describe a plane by saying everything perpendicular to this one normal vector. This is our way of describing an entire plane with one vector. It's weird to do this exercise in R2 because we have a very convenient way of describing the direction with slope, with one vector. But we use one vector to describe a line because it's only one line. But a plane is made up of two lines. There's a change in the y direction, there's the change in the x direction, whatever they happen to be. There's two lines that are describing this plane. But we can describe an entire plane with one vector. This is an important idea. This is why we care about standard form suddenly when we're talking about planes. The coefficients in the standard form tell us a vector that is perpendicular to the plane. The reason that we care about that is that gives us another way to describe a plane. So we can describe our plane with two vectors. So we can say the plane is every combination of these two vectors, or we can describe it as everything perpendicular to one normal vector. Describe the plane with two vectors, or we can describe the plane with one normal vector. This normal vector is perpendicular to both of these. That almost worked. So I'm starting off with our goal for vectors, which is the next big thing. We're starting off with the goal, one of the goals of dealing with vectors. And vectors are our next big thing. Good Friday topic, just kind of like bring up a few things that are going to be coming up, and then send you off into chapter 13, which we'll talk about in more detail next week. Any questions? Comments? Not Ramon? Yes. Yeah, so what we're getting at here is that to describe a plane, I just need two non-collinear lines. And the word line I can replace with vector. So I can say this plane is every combination of those vectors u and v. This is how we do it already. The xy plane is everything that has a 1, 0, 0 and a 0, 1, 0. It's the span of all those two vectors. So we could also describe the XY plane as everything that's perpendicular to the z-axis, everything perpendicular to 0, 0, 1. So when I say the span of u and v, I mean every possible linear combination of u and v. If I take any combination of u and v, that's going to stick us in the plane, stick us to the plane that contains those two vectors. That's two vectors defining a plane. That's two lines defining a plane. The other way we can define a plane is saying everything perpendicular to this one vector. This is what I want running in the background while you start working on vectors. At this point in your mathematical career, you all have different vector backgrounds. Some of you are engineers, and so you're in a physics class, and you've done the mechanics part of physics, where you talk about vectors. Some of you have took linear algebra at some point, and in linear algebra, you talk about vectors. Some of you took an engineering statics course, which is like, oh, hey, remember physics? And you're like, oh, yeah, we're going to do that again. Here are some vectors. And sometimes the first time you see vectors is when you get to count 3. Math is weird to order it so well. Yes. Yes. An easy example, like how we would find the vector. So the first thing you would do is take n and then just find something perpendicular to that. We need a little more mechanics behind to find, but we would find something where the dot product is 0. That's what we try to make. And then we would make another one with the dot product is 0. But we haven't talked about dot product. So yes, but not yet. I guess I'm only doing half of the it's dangerous to go alone. So I'm not like, well, it's dangerous to go alone. Take this dot product. I'm just like, oh, it's dangerous to go alone. See you. Aren't you going to give me something to help? Nope. Okay, so yes, we can, but we don't know right now. Collectively, we don't know yet how to yet. But we'll get to that. Any questions? So your job this coming week, we're going to be learning about vectors and catching up on the work in chapter 12. We're moving into chapter 13, catching up on the work in chapter 12. As you walk around in the world, I want you to see surfaces and imagine describing those surfaces as functions. Sometimes it's easy, especially in a school, because there's lots of tables and they're all just like little chunks of planes. But try imagining some different surfaces that have some texture to them. And then start thinking of vectors. Start thinking about vectors. As you're walking along, think about what your vectors are. What's the direction vector? What's your acceleration vector? What's your position vector relative to some location? All right, that's going to do it for today. That's going to do it for this week. Everybody have a good weekend, and thanks for playing.